Now.
Welcome back, everybody, to the online seminar series, Machine Learning Needs Mathematical Optimization. Today is our session number 50, so we have a round birthday, and we are very happy to have today as our presenter, Zhang, who is an assistant professor in computer science at the ETH Zurich. And he works on machine learning and topics like cost efficiency, trustworthy, so topics that are very relevant to in machine learning nowadays. So he did his PhD in Wisconsin-Madison, and then he was thank you, Emmanuel. So he was a postdoctoral student in Stanford, and now he's back in Europe. His research has received prizes from SIGMOD Best Paper Award and SIGMOD Research Highlight Award, Google Focus Research Award, and he received recently an ERC grant, starting grant. So we are very pleased to have you today. His publications are from Science, Nature, Communications of the ACM, and etc. So, Che, the floor is yours, and thank you very much for joining us today.
Yeah, thank you so much for the invitation and introduction. Hi everyone. Today I will share with you a little bit what we have been working over the years, and really give you kind of some thinking about how I think this decentralized learning paradigm is really moving forward, and more like a call for help, right? Because there are so many things we have no idea how to solve. If the community can actually come together, I'm sure we have a very bright future. So we see machine learning really everywhere, right? From the small things like a single sensor, right, to bigger things like smart car, right, your drones, right, your smartphone, even to a smart city, right? So today I'm not going deep into how many applications we can do using machine learning, but I will focus on maybe one problem that I think machine learning is really happening today. So among so many different problems that machine learning happen today, the thing that we are particularly interested is the cost, right? Because from our experience working with so many people in industry and academia, something that really surprised us even in the beginning is essentially machine learning today, if you think about it, has a very serious cost problem. So let me show you three different examples, right? So this is actually one paper we had earlier this year at KDD, where we actually train a pretty big recommendation model, right? This model has 100 trillion parameters. So our original goal was, okay, let's take the biggest model out there and make them 10 times bigger, right? So once you have this, right, building a system becomes a little bit non-trivial. But if you think about, okay, how much money do we really need to spend to actually train this model for one day? 100 trillion parameters is like 400 terabytes of data, right? Either in memory, on hard drive, whatever. So how much money do we need to spend in training those models for one day? And here are multiple choices, right? So I mean, just think about what would be your answer. So I don't know what that answer is, but what actually happened actually surprised us in the beginning a lot. We actually do this exercise, really try to run this model. So what actually we spend in a day amount to $40,000. If you think of how much that thing really is, it's like these two amazing students take a very fancy car and just burn it in a day. And you can actually read more in this Google blog post about all the machines that we have been using in that day to actually make it happen. So it's actually pretty expensive. And this is not only the single model that's expensive. If you think about GPT-3, we have been looking at this and see this fascinating capacity that this model has. So the question is, okay, assuming we want to train a single model, similar to GPT-3, 175 billion, but 100 times smaller, okay? We will not want to train the biggest model. We want to train a model that's 100 times smaller for one run. Onto this public cloud, I mean, at which orders of magnitude are you going to spend? Yeah, again, think about the answer. So what you would have here is actually probably spend around $5,000 to just train a model that's 100 times smaller than state of the art. And just a couple of weeks ago, there's a kind of startup try to brag about, we actually can train this under $500,000 for a 30 billion model. If you think about people are celebrating because they bring the cost down to $500,000, you know how expensive the whole thing really is. Even for the smaller model, right? So training that on like 1.3 billion parameters, it actually requires you to have 2.4 teraflops and running non-stop for 5 days. And the cost of learning doesn't really only come from computation and also storage. So this is actually another application we are building together with a startup in Zurich. Our goal is really try to construct this global hub of network restoration. A more concrete way of looking at this is for every single patch that satellite or drone can actually give you the cover of whole Earth. We actually want to detect all the natural resources. We want to count how many trees that we really have on our Earth. So more concrete on the learning side, the thing that we have is a whole bunch of images that look like this. And then the label that we want to provide is actually the small circle in the middle, right? So to tell you, okay, this is a tree. How much money do we need to spend to label one image like this, label all the trees, right? So again, here are a few number of choices. What ends up happening, especially in our application, is we won't be surprised if every single image costs us $10, right? And then if you think about how many that we have to actually label, we have more than 1 million of those images that we could label. We don't have to label all of them, but we actually don't know how to pick the core of that 1 million images to actually label to do the best machine learning applications. So by looking at these 3 concrete examples, I hope I have convinced you that machine learning today really has a cost problem. So what should we do about that? So over the years, one thing that my research group have been doing is really looking at the cost problem of machine learning. It's actually a very difficult problem because you have to take a holistic view because machine learning and AI are actually expensive for different reasons. On one hand, there is the computation and storage cost, right? Those big models, really, they need a huge amount of compute and huge amount of storage. And what coupling with that is actually the infrastructure cost. So to actually run 1 teraflop, you need to pay that much money on the public cloud to actually hold 1 terabyte in memory inside your in memory for 1 hour. You need to pay for that. So these two things coupled together give you this very expensive training cost. But on the other hand, there's also the cost of building those applications. Human who's building those are expensive, right? The cost of data, acquired data, annotated data, clean data is also pretty high. And then if you think about regulation, there's also the compliance cost, there's the EU AI Act, there's a whole bunch of GDPR stuff, right? So people start to care about fairness, robustness, all those important dimensions beyond accuracy. And there's a huge cost to really try to understand how can we build our application to make sure it can actually deliver something good to our society. And then there's operational cost. Once a model is being deployed, there's a monitoring cost, there's a test, adapt, and scale cost. If you look at all this together, this is what people are facing today, building machine learning applications. So over the years, we have been looking at these 5 different costs, and our research can be kind of organized into these 2 different categories. So we have a whole bunch of work, try to look at the first 2 dimensions, right? We really try to ask, okay, if you look at everything that is making machine learning training expensive today, is it really necessary, right? Do you really need to send that much information between different machines, right? Do you really need to build those very expensive interconnections between those machines? And what we kind of realized over the years is not really, right? So the way to achieve that is not trivial, but if you kind of co-design these 3 different dimensions on the training algorithm about how to do optimization, on the data ecosystems, where the data is, how to have this machine learning integrated into the data ecosystem, and build the right hardware for your kind of application, you can actually unleash a whole bunch of great systems to actually bring down the cost, right? So in terms of the thing that we have been doing, we look at this in the region of 100 to 1,000 machines and try to understand how can we do compression, decentralization, asynchronization. We have been helping a whole bunch of systems, right? So for example, if you go to PyTorch Lightning, it's a great system, right? You can actually use some of the things that we have been building with this single lines of code using a strategy called BAGUA, right? You can then start to enable those system relaxations at different parts that you are doing communication. Right? If you're using OpenGauss to database, right, it's something that you can already kind of use. So second thing that we have been looking at is by looking at the DevOps process of machine learning. Essentially, the fundamental thing that we have been asking ourselves is, can we make the process of improving, testing, monitoring, adapting, and scaling machine learning applications as systematic as possible and also as data efficient as possible? So what we realize is many of those steps you see here can be made very systematic. And there's quite a lot to save if you give your user a very strategic and systematic guideline about what to do next. So what we have over the years is this end-to-end process of machine learning DevOps. So today I will spend most of my time talk about the performance side. How can we scale up machine learning training? And the key thing that we have been exploring over the years is how can we enable this decentralized paradigm of training machine learning models. So if you look at last decade, right? So one thing that actually drive machine learning scaling is by making this infrastructure as centralized as possible. What do I mean? So the high level goal is you go to data center today and try to rent a whole bunch of machines. Those GPU cards, they are really closely coupled. Within each machine, you have, for example, NVLink, right? So they give you 900 gigabyte per second communication between all those cards. If you think about how fast those machines can communicate, first one, everyone can communicate to each other, right? You have this fully connected topology. On the other hand, we are talking about 10 gigabits to 100 gigabits network connected by a latency less than 0.1 millisecond. So people are building this infrastructure more beefier and beefier and beefier by putting in stronger and stronger connection between those devices. And this really enables this fascinating paradigm of doing learning, that is data parallel SGD, right? All the machines at every single round, they are going to exchange information between all of them. This algorithm is just fascinating, has so many good properties. It's very stable, it's very easy to debug. Well, it's easier to debug, right? So, and on the other hand, because people are building those fast connections, those algorithms, centralized SGD, is also pretty fast. So this is a sweet point of centralized learning. If you look at all the fascinating things we have in machine learning today, I could argue many of those are actually enabled by this paradigm of training. It's really, really successful. But on the other hand, it also brings a question, that is, can we make this infrastructure weaker? Do we really need all those fast connections between those machines? Because once you decrease your dependency on how closely coupled those devices need to be, you start to have an infrastructure that becomes cheaper, cheaper, and cheaper. You could have a group of machines that being connected by reasonable network that are close to each other, but you do not have the super fast link. Instead of have 10 gigabits, you have 0.1 gigabits, right? So can you do that? Because once you can enable something runs on this infrastructure, the ownership cost of the infrastructure is going to be much, much lower. And also, do I really need those machines to talk to each other? If I have a whole bunch of geo-distributed machines, can I actually train something over those infrastructure? Can I enable a paradigm that everyone at home that contribute a single GPU and together we get it done? If you think about this, it actually brings this kind of evolution of the infrastructure from a data center to the multi-cloud setting, right, to a geo-distributed home setting. And what we realized over the years is once you start to weaken your communication infrastructure, you start to need this different type of algorithms to actually make it happen. So before I talk about more on the technical side, let's do another quiz, right? So where are we today? What has been the progress that we have been making, and putting them together, what have we as a community of our group? So this is actually one quick example. It's really something that we have been doing this year and try to put together a whole bunch of things that the community have been working on over the years and try to see how fast we can actually push the decentralized side. So assuming you have, for example, 32 V100 GPUs, and assuming the task that we want to do is we want to fine tune like a reasonable model, like GPT-2 1 billion on, for example, Wiki text 2, something like that. And consider these two different things, right? So you have one setting which is centralized. I rent all those machines on AWS, right? I have, for example, 1 GPU per instance. I have a 10 gigabits network, and I run mega. So this is one setting. So second setting would be, okay, let's put this network on 8 different distributed regions. Okay? So you can see their communication topology here, right? So their connection is roughly like 0.5 gigabits, right? Roughly like that, right? Depending on where the machines are, right? The communication latency is around like 1 millisecond to 200 milliseconds. Essentially 20 times lower bandwidth, more than 30 times slower latency. So the standard kind of data Parallel SGD, right? Cutting our model into different pieces. We do the pipeline parallelism. We also pieces. If you look at the two sides, so we only care about total training cost. And cheaper as a decentralized infrastructure need to be to make economic sense. The other way to ask the question is how much time slower will the decentralized setting be compared with a centralized setting to reach the same accuracy? It reflects your communication, you can do computation, do synchronization, but our goal is to reach the same accuracy. Right? How much slower this decentralized setting? So here are multiple choices. So for your answer. So we kind of realize years is by putting together all the great work we are building 1.5 times for this application. So, and this actually enables something, in our opinion, really fascinating, because this decentralized infrastructure, even though its communication is much, much weaker, it will not slow down your application too much if you put together what the community already knows how to build and also try to construct the system carefully. So for us, that really bring this hope to us, that try to take this centralized infrastructure, which is quite expensive today, and try to bring them into a decentralized future. So we are kind of very, very excited about this. So today, let me kind of tell you a little bit about the thing that we have been learning here from the community and a little bit about ourselves, and then try to tell you what I think where we are and how we should move forward in the future. So we have been looking at this evolution of the infrastructure over the years, bring this very fast interconnected network into something much, much like slower. So we kind of learned several lessons over the years. The first one is the latency and the bandwidth of the underlying infrastructure really requires a variety range of technologies for performance. You need to deal with asynchronization, comparison, decentralization. And the second lesson is for each combination of those relaxation techniques, there actually exists an SGD style algorithm that has two different properties. The first one is they actually converge under very mild condition with the same convergence rate as SGD for smooth non-convex functions. And second is it actually works. It actually works in the sense that if you give me a realistic model, I could reach the same accuracy or the same loss given a very similar number of iterations. So this is actually not that easy. We have been doing our homework since 2015, try to study a whole bunch of things about how to design algorithms for different settings. But on the other hand, this community, right, really come together to have a whole bunch of much more amazing work to really understand these three different dimensions. But together, right, so there is actually some algorithm for this each different ways to relax these relaxations. And third lesson that we learn is we really try to build a system. It is actually possible to build a single system to support all those algorithms efficiently, right? So here's a thing that you can learn, like you can actually try to play with, is this system called BAGUA that we have been building, right? If you are using PyTorch Lightning, right? So this really just this one line of code to really enable all of those algorithms and try to optimize them in an efficient way. So this actually gives you improvement even on the data center network, right? But also on a slow network, it gives you even more speed up. So the first lesson that we learn is if you try to move away from data parallel into model and pipeline parallel, you kind of need to have new algorithms, okay? But still, so it's still possible to accommodate slow networks, right? So I will actually talk about a little bit about our effort here recently about how to kind of distribute this workload, the single model, to a geo-distributed machines. So today I will talk a little bit about these two different things. I will talk about the system and the theory side of the data parallel paradigm, and then I will talk a little bit about this pipeline parallel paradigm. So how should we think about data parallel SGD, right? So I think everyone here are really familiar with this. Essentially, the way that we think about it is there are three different players in the system. There's a data source where you get your data, and then there's your computation device where you do computation, and then there's some piece of storage so to store the model. So how SGD works, right? So essentially, okay, I read a data example from my data source to my computation device, and then I read my current model, and then I compute my gradient and update my model, right? So this is pretty much what it is. And when you do data parallel SGD, you have multiple of those workers. Each one of them are looking at maybe a partition of the data, or maybe the whole different data, maybe the same data set with different sharpening strategy. But you have these different parallel workers, and every single time you update your model by just averaging them, and then you do your SGD stuff. If you think about this, right? So essentially, it's a very simple dynamics with full length of code. You synchronize your model between all those machines, and everyone just get their data, get their gradient, and update their local model. You keep doing these 4 steps again, and again, you get the model in the end. So if you think about this algorithm, right? So what we have been interested in is try to understand these 3 different questions. The first one is if you look at this communication primitive, how can we make them weaker? What is the minimal requirement for a synchronization primitive that to give you the same convergence behavior from SGD? And the second question is every single time I move my data between these different players, what is the precision of data movement that I need to actually achieve the convergence? So here we have 3 different data artifacts. We have the like essentially your data, you have the gradient, and you have the model. Right? Every single time you move each piece of data between different workers, what are the precision that you need? And also, whenever you are getting the data, right, you need to have certain notion of randomness in how you get the data. You cannot have this worst case systematic scan over your data that's going to screw up your convergence. What is the minimal requirement of randomness in data shuffling, right? If you look at this full length of algorithm, so these are, in our opinion, 3 fundamental questions that we have to understand if you really want to relax this algorithm. So in the baseline, right, we have our textbook centralized, synchronous, lossless SGD, right? If you look at what it is, it's essentially say, okay, every single time I synchronize, my primitive is a synchronous average operator, and every single time I move my data, I do not do any lossy compression. Every single data movement is lossless, right? The high level idea is that you distribute this gradient computation to multiple workers, and then you synchronize your workers with in a centralized way, right? And it doesn't mean you need to have this logical, like it doesn't mean you need to have the server in the middle to aggregate those, you have to all reduce. But from the information perspective, right, every single time that you synchronize, all the machines talk to each all other machines, right? So you have this all-to-all communication pattern in the end. So mathematically, right, so this is what you have at every single iteration. The conversion rate look like this, where T is number of iterations. And then if you think about how the system actually perform, you have the 2 different stages. You have the computation stage of your gradient, and then you have the communication stage of the gradient. So when we really relax this algorithm, the thing that we want to achieve is we want to have an algorithm that keeps the convergence speed, at least in the big O sense, but on the other hand, make the system side faster. So there are actually lots of things you can do, right? For example, you can actually quantize this communication, right? So the community really come together to actually study this for the last decade and have really a lot of fascinating results. Every single time you synchronize, you still do your average, but on the other hand, every single time you move your data, right, you send in this lossy, compressed version of your data. So there are a lot of smart things that you can do, but this is just one baseline algorithm that every single time you commit your gradient, you quantize it, you sum it over, you quantize again. This one doesn't even have error compensation. But even with this, you are going to have a convergence rate that looks like this, right? Where the epsilon is really the error caused by the quantization itself. But you can do a whole bunch of fascinating things. You can do error compensation, you can do a whole bunch of things to really make the convergence even faster. But even with this very naive algorithm, you get something that looks like this. And then you can do asynchronous communication, right? When you normally do average, right? So those machines do not wait for each other. You have this asynchronous notion of average, but you do not do any data compression, right? In this case, every single machine going to have access to a stable version of the gradient, right? So you have this another higher level term in the convergence. But again, you can do much better than this, right? So, and you can also do this in a decentralized way. We have been kind of playing with this since 2017. Essentially, you have this not fully connected topology, right? For example, all those machines can form a ring, and every single time you talk to each other, you only talk to your neighbors. You have this decentralized notion of average, right? Where you only average the model between those local workers. Even this algorithm gives you something that kind of interesting. It still introduces certain term in the convergence, depending on the network topology, that could be pretty small, even theoretically. And empirically, and there are actually cases you won't see the difference. And you can start to put all those together, right? What if you want to decentralize and quantized communication pattern where every single time I synchronize, I have this decentralized average, and every single time I move data around, right, I have this quantization, right? So this makes your algorithm a little bit harder to do because you do not want to do this lossy compression on the model. You want to do the lossy compression on the updates of the model, right? So you kind of need to maintain this previous model state, and every single time you communicate, right, you communicate the difference, right? So in this case, you have a little bit more complex algorithm, but again, you are able to get something that looks like this, right? So there's a higher order term that's introduced because of the relaxation you are doing on the communication side. But again, even theoretically, it won't have a big influence on the convergence speed. So there are actually more things that you can look at over the years. We kind of try to summarize a little bit about what we are doing, but more about what the community is doing over the years, and put into this very, very small monograph to really talk about these three different dimensions and a little bit about theoretical analysis. You can actually see more about the theory like in this very small monograph. But another thing I want to talk about after this theoretical thing is really now we have this collection of algorithms that allow us to relax this communication of this standard SGD algorithm. How can we translate those flexibility on the algorithm side really into the performance improvement from the system side? Because this question is really not that trivial. So analytically, it's pretty clear what we should do. Because we have this family of algorithms, right? So you can think about them as, okay, they have comparable theoretical convergence rate, and often they have comparable empirical convergence rate, right? So, but they have very different time per iteration profile for different network conditions, right? If you think about network condition, right, you can organize them into three different dimensions. There's latency, there's bandwidth, and then there's whether there's like stragglers type of things. For each of this, right, for different type of algorithm, for example, asynchronous algorithm works really well when you have a heterogeneous network, when the machine are not, or network not equally fast. When you have this decentralized kind of type of algorithm, it's very good for high latency network, right? Because you only talk to your neighbor, you do not need to have global information propagation between all those machines. When you have this quantization type of thing, right, it kind of works really well for low bandwidth network. From the system trade-off side, it's pretty clear. But the challenge is really how to put them together and how to make sure users have access to all those amazing algorithms that the community have been building over the years. Because if you look at this landscape of machine learning system today, right, you see this gap. On one hand, there's a whole bunch of amazing system people are building, right? So there's a Honeywell, there's a BAGUA, right? It's enabled this kind of distributed learning paradigm that people have been doing. And on the other hand, we also know how to design as a community this different type of algorithms to relax the communication. But one gap today is most of this amazing system we are using doesn't really support all those amazing techniques. So many of those systems, they support some of the asynchronization techniques, so they support some of the compression technique, and that's it, right? So the thing that we want to do in this project is really try to build a distributed learning system with state-of-the-art communication optimization techniques. At a high level, this is our wish list. We want to take all those different ways the machine can actually communicate. And then we build a system that user tell us, okay, I want to do asynchronous, decentralized, lossless communication for my algorithm. And we compile the whole thing into a modular way, into this primitive, and make it possible for you to apply it to your deep learning stack without really thinking about how to optimize the communication pattern and also how to optimize your execution of your training process with this communication primitive. So this is actually what we want to do. So it's actually not an easy journey. It kind of takes us 2 years to actually do a little bit. On the system side, here's a challenge. A naive implementation of those algorithms might not give you any observable speedups, right? To really fully take advantage of this flexibility provided by the centralization, right? You kind of need to carefully optimize the system implementations. Because the baseline is really, really strong. If you think about what the existing system is trying to do, no one is going to implement a vanilla SGD algorithm, right? If you think about what a vanilla SGD would do is, okay, I do the backward pass of the last layer, I communicate my gradient, I do another layer, communicate my gradient, so on and so forth, and then right, I update my model, I proceed, right? But no one really implements this. Right? If you think about how, for example, Honeyworld or Torch DDP is trying to do, they try to do very aggressive batching, put all those computation together and put the communication together, right? And then try to manage the dependency between communication and computation to really try to hide as much communication as possible for this algorithm. And if you look at how PatchPS, PatchPS is doing this, right? It's a very interesting kind of like scheduler to kind of partition this communication into smaller pieces, and they try to do this very aggressive scheduling and try to send kind of send a piece of data that's going to be used most recently in the future, right, as early as possible, right? So the community has been developing a whole bunch of things that you can do to make the system faster. When we want to design a system to support other algorithms, Honeyworld and PatchPS is actually our baseline. We want to improve all those, not improve this vanilla implementation of SGD. But one challenge is because now we want to support so many different algorithms. They have different computation patterns, they have different communication patterns. We cannot conduct optimization as this system is doing by assuming you are working with one algorithm. We don't really have a full control on the algorithm side. And we do not want to optimize those algorithms one by one because it's going to give you a very fragile system. So essentially at a high level, we kind of try to do a little bit exploration about whether we can have a modular design in the system. Essentially, we hope to have a modular design to accommodate the diversity of different algorithms and communication patterns, right? And lead to an optimization framework that apply automatically to an algorithm implemented in this BAGUA framework. So we think about this training task, right, as these two different components. You have your data and you have this computation graph, which is your neural network. And then from the user perspective, all you need to do is just wrap up your training script into the BAGUA framework and specify what algorithm that you want to use. If you are doing Lightning, you can just add this one line to say, okay, the strategy is, for example, low precision decentralized, okay? As you can see like from this example. And what the system is trying to do is each algorithm is being specified by a whole bunch of forward and backward hook associated with each of this layer. And within every hook, you can use a whole bunch of communication primitives that we optimize for you. Okay? For example, you can say, yeah, so there's one primitive for low precision decentralized synchronization. Right? They look very similar to MPI primitive, something that you can actually use as if they're all reduced. And then what the system is going to do is once you specify your algorithm in this way, it try to automatically optimize this execution for you automatically. For example, if you have the decentralized low precision algorithm, right, in your algorithm specification, what you are going to have is all those different stages that come together, right? And then what the system is trying to do is really try to automatically batch them together, try to automatically hide communication behind computation in the correct way, correct meaning that you are going to get the same result in the end, right? Try to do that automatically for you as a user. So again, there are a lot of system kind of details about how to really make it work, right? So it's very hard to actually compete with Nico, right, which is opted by NVIDIA for years. It's very hard to compete with Hoverworld and BAGUA, which actually optimizes really well for the vanilla kind of SGD algorithm. But in the end, it kind of works. So this is actually what we have on more than 100 different GPUs, right, connected by different network conditions. So in terms of convergence, right, so here the x-axis is actually number of steps, y-axis is either the accuracy of F1 score, right? So as you can see, for each different scenarios, there is some of the communication compression thing, right, relaxation thing that can give you essentially the same convergence behavior. But on the other hand, on the system side, right, you can actually outperform very strong baselines. We are not talking about the Hoverworld 32 bits. We are talking about Hoverworld with a little bit of communication compression into 16 bits. It's kind of very solid baseline. Even under data center network, right? Supporting this very diverse collection of algorithms can give you pretty significant speed up over existing systems. And this is something that you can reproduce by yourself. And when we talk about slow networks, it's getting even more interesting. So for example, when you have a network with very small like bandwidth, right, from the right to the left, we kind of decrease the bandwidth of the system. You can see the pink curve, right? So it's a Hoverworld, right? Whenever the network becomes slower, the system becomes slower, right? But on the other hand, if you do more aggressive compression, if you do a little bit more aggressive asynchronization, you can have this collection of algorithms to allow you to navigate different network conditions. Again, we are not championing one algorithm over the other, right? So all we want to provide is you have this continuous spectrum of algorithms that you can actually pick given your network condition. So the same thing happens for latency, right? So here from the left to the right, your latency becomes slower, slower, and slower, right? If you do nothing, right, as you can see for the pink curve, that's your Hoverworld, right? But you can actually like your system in different ways to give you this different type of choices that you could make given your network condition. So this is about data parallel, right? So now let me tell you a little bit about this pipeline parallel thing because it's kind of very, very interesting. So what we have is like this. Instead of having all those workers working on the same model, right? Essentially in pipeline parallel, because the model is too big, you have to partition this model into different machines. So for example, here we have this transformer model. We start to cut them into different machines. So there are two different types of communication you need to have. You need to have the forward activation communication between the two machines. We want to do the forward pass. You also need to have this backward kind of gradient communication. We want to do the backward pass, right? So of course, you still have your model gradient, right, to do this like a data parallel thing. So one thing that we are curious about is we have been doing a whole bunch of work together with the community about how to do the model gradients in the green side. How can we deal with this forward compression and backward gradient? How can we compress those? So this is actually something that is very interesting because if you think about what's the difference between this forward activation, is there's a huge amount of non-linearity associated with that. Because whatever that you compress, you need to pipe them into a nonlinear function, which is the next layer, right? So you are going to have very different behavior from the system when you start to compress those activations compared with compressing the gradient. So even when you have one layer, right, which is you have a generalized linear model and you compress your data, even that is not that trivial. So we start to play with that in 2017. But even for like linear regression, it's kind of not trivial, right? So assume you want to solve the linear regression problem where A is the data, X is a model, B is a bias, right? So what you are going to have is, okay, my gradient is going to look like this. But just looking at this formula, right? One thing that we can realize immediately is it has a nonlinear dependency on your data. So the consequence of that is that if you have an unbiased estimator of your data, it doesn't give you an unbiased estimator of the gradient. So this actually causes problem in practice, right? If you just do this kind of naive random sampling of like naive quantization of your data, you are going to see this guy, even for this very simple linear model. But for linear model, you can do something. Okay? So you can actually say, okay, instead of having these two independent samples, like instead of having like one sample, use it twice, you can just have two different samples, right? You have one unbiased sample for the first time you use data. The second time you use data, you have another unbiased sample. This one gives you 1 bit overhead on the system side, but give you something that actually works pretty well, right? So this is about tomographic construction. This is a little bit about compressive sensing, right? It can actually give you something. And if you have a nonlinear model, and if you really want to go deep into the structure of the nonlinear model, you can actually approximate the whole thing into a k-degree Chebyshev polynomial. It's kind of, you have k different samples, then you have unbiased estimator of the gradient. For compressive sensing, it turns out HT is kind of pretty robust to this type of thing. But we are not happy about this, right? Because it kind of assumes too much structure, right? So when you have these multiple layers, how can we do activation compression? So here, the thing that you have looks like this. This is actually like two different layers, right? Where A is one layer, B is the upper layer, right? You have two models, XA and XB, right? You put them together. So what can we do here? So again, if you just compress your activation in the unbiased way, you will have a biased gradient. And that's something that you're able to see in practice. So that's very similar to the one layer case. But here, when we talk about these multiple layers, we actually do not have too strong a structure about the problem. So what should we do? The short answer is we don't know, right? But we have some early attempt about how to accommodate this problem. One thing that we could do is, because you are going to do multiple epochs over your data, so let's look at the same example across epochs, right? For these two different pictures across different epochs, what you are going to do is going to do the forward pass, right? So given different models. And then if you compare the difference across epochs, interesting could happen, because the difference of the activation of the same data example across epochs in expectation should start to diminish. And the high-level idea is then we can actually try to quantize the difference of the activation across different epochs instead of directly compressing the activation for a single data example. The high-level idea is really, when your model converges better, if you look at the model change across different iterations of the same data, the change of the model will become smaller. And then if you look at the same example, the change of the activation will also become smaller. And then the difference will also be smaller because the change is smaller. Your quantization error will also be smaller because most of the quantization thing, they actually depends on the norm of the data, right? When your difference becomes smaller, your quantization error starts to decrease, then you converge better, right? So all you need to do is to control your precision of quantization to close this loop. And that's something that you can actually formally prove under a whole bunch of kind of assumptions. You can actually prove if you compress the difference in an unbiased way, you are able to have a 1 over square root of t convergence under mild technical conditions. And it actually works in practice. That's actually one of the building blocks of this decentralized experiment that we have been doing. Essentially, if you do 3-bit forward, 6-bit backward, and 4-bit data parallel gradient, you are able to have something that actually converges pretty well for fine-tuning workload, right? So here the blue curve is a full precision communication, and you have this green curve, which is the compressed version, and you have the orange curve, which is actually directly compressing your activation in an unbiased way without dealing with the diff. So as you can see, if you just compress the whole thing, right, it actually gives you a pretty big gap. So from the system side, it can give you something to actually accommodate a whole bunch of bandwidth conditions, right? So as you can see, if you go from 10 gigabits network on the left, right, all the way to, for example, 500 megabits, right? So you have this 1.5 times slowdown, right? Because now every single part of this communication kind of compressed. So this is actually all I have for today, right? So over the years, we have been actually work together with the community to really try to understand these problems, and we learned a lot. But on the other hand, there are a whole bunch of things that we have no idea how to do, right? We don't even know how to compress this activation in a forward path in a principled way, right? So this talk is really a cry for help, right? So how can we relax the communication? How can we design new algorithm, right? And how can we enable this decentralized future of machine learning, right? So yeah, so like that's actually all I have for today, right? So I'm happy to answer whatever question you have. Again, thank you so much for the invitation. Yeah, thank you.
Thank you very much, Chef, for your very insightful presentation and say the problems that we are facing in large-scale learning problems. So we open the floor for questions. So if you have questions for Chef, please raise your hand, and then we will give you the rights for. Yeah. So Sureya. Yasoni is going to give you the rights to the camera and the microphone.
Hello.
Hello.
Hello. So you hear me and see me. Actually, now I'm in the lecture teaching, so I projected your slide. My students also listened to your presentation. Thanks for this interesting talk.
Cool.
I'm in the machine learning course. So first we listen the presentations and then I continue my lecture. I'm a professor in mathematics department in Bahçeşehir University in Istanbul in Turkey. And I mostly work on ensemble learning and ensemble pruning through optimization theory. So I intuitively feel that in your work, when you combine different data sets in your formulation, you have weighted average. So it seems that you are doing a kind of ensemble aggregation in that formula, and you update it according. Also, I feel some sound from meta learning. So you correct the steps by learning different portions of data, and you also kind of boosting involves in your whole paradigm. Am I correct? Or if I'm not, so I'm wondering the relation between these things in your centralization, decentralization, all these things, and in those combinations. And also another question. I'm wondering where is that non-convex functions appear in the formulation? I think you didn't show, or I missed it. I'm not sure.
So okay. So I mean, these are very insightful questions. So the first one about the relationship between ensemble and distributed learning, the short answer is I don't know. But we have been looking at a whole bunch of really interesting examples by the community. For example, there's one paper. What they do, it's a very interesting paper called Lo-Fi. So what they do is okay. So you have all those different partitions of the data. What they do is okay. You just learn them independently. At the end, you have a whole bunch of models, right? And then I just kind of either I do a sample on the model, or just average the model in some weighted way. So this actually try to push this distributed learning directly into ensemble, right? And they actually show in many applications this actually works reasonably well, right? So you can think about the one extreme when you do not do communication at all, it's just ensemble. On the other hand, we try to communicate a little bit more to really have some consistency notion between those different experts, right? So I think what's interesting is there must be something in the middle to balance these two things. So that we have no idea what that thing is. And kind of very interesting to kind of explore deep connection between these two paradigms. I do believe there's something here. I just don't know what it is. Yeah. And second, for the non-convex thing, yeah, so it's really coming from the structure of the neural network, right? You have multiple layer, every single layer have a nonlinear function, and together you have something non-convex. Yeah. So I mean, this ensemble thing is really, really interesting. So we have no idea how to deal with that, and we see so many different examples. For example, those mixture of experts, right? So also make your training process much easier, right? So we see this very interesting interplay between ensemble, mixture of expert, and also distributed training. We just don't know what the connection really is. Yeah.
I just came to my mind now. Do you also consider the diversity between these learners when you create these?
Yeah. So for us, we do not okay. So yeah, because we deal with distributed learning, right? So what we do is we have the whole data set, we partition it, or we shuffle it to make sure everyone hopefully agree with each other. So we try to have IID thing, right? Like between those workers. But you don't have to, right? If you know, okay, my data is not, you can actually do some of this compensation between those workers to kind of take into consideration of that. This go a little bit into the federated learning side, right? Where your data is inherently non-ID, right? So you are going to have a different collection of algorithms just for that. Yeah. So depending on what assumption you have on your data. Yeah.
Okay, thank you.
Yeah,
Thanks a
you.
lot.
I guess there are no more questions from the audience. So it was very interesting to see your talk today. Thank you very much for coming.
Yeah. Thank you. Yeah. Bye.
Thank you. And to the rest of the people, we see you next week with the next speaker. Thank you so much. Thank you, Alexandro, for the words. Thank you, Sebastian. Thank you, Belen. Thank you, everybody.